Thanks very much for joining us. My name's Peter Bartlett. I'm the Associate Director of the Simons Institute for the Theory of Computing. We're a collaborative research institute for theoretical computer science. We were established in 2012 with a grant from the Simons Foundation. And the Institute brings together the world's leading researchers in theoretical CS and related fields, as well as the next generation of outstanding young scholars, to explore deep, unsolved problems about the nature and limits of computation. So it's my great pleasure to welcome you to the inaugural presentation in our Breakthroughs lecture series, highlighting substantial advances in the field of theoretical computer science. And today we're presenting the first of two Breakthroughs talks that we'll have this summer. We're looking forward in the fall to being able to convene the series in person in Calvin Lab. So before I introduce our speaker today, let me mention we'll have an opportunity for audience members to pose questions later on. So we ask that you hold your questions until then and use the Q&A function in your Zoom window to do that when the time comes. All right, so our speaker today is Virginia Vassilevska-Williams. Virginia is the Stephen and Renee Finn Career Development Associate Professor of Computer Science at MIT. She holds a PhD from Carnegie Mellon University and was previously on the faculty at Stanford. She's been a member of the Institute for Advanced Study. She was a postdoctoral fellow in computer science here at UC Berkeley. Her research is broadly in the design and analysis of algorithms, focusing on problems in graphs, such as the shortest path problem, in matrices, computing matrix products, which we're going to hear all about. And she's also interested in computational social choice. Her talk today is about her recent breakthrough in the computational complexity of matrix multiplication. It's entitled A Refined Laser Method and Faster Matrix Multiplication. Welcome, Virginia.
Thank you, Peter. It's a great pleasure to join you today and to tell you about this work. As you can see here, I have a comic about it. It's a real comic that is on SMBC, and it's titled Mathematicians Are Weird. So we'll see exactly how weird we are. All right, so I'm going to talk about matrix multiplication. So this is the matrix multiplication problem. Matrix multiplication was defined by Cayley in 1855. We're given two n by n matrices, A and B, whose entries are from some field. Think of the real numbers, the complex numbers, and so on. And you want to compute another n by n matrix, C, so that every entry of that matrix is the following polynomial and the input matrix entries. So Cij is the sum over k of aik times bkj. And one of the main questions that we want to answer is how many operations over the field, so the products, sums, divisions, and subtractions, do we need to do in order to multiply two n by n matrices? So people define this quantity omega, it's the exponent of matrix multiplication, and is the smallest real number, so that n by n matrices can be multiplied in n to the omega plus little o of one time. So it's some constant. We know omega is at least 2 because we have to output an n by n matrix, n squared entries, and it's also at most 3 because of the definition. So in the definition, we see there's n cubed things we can compute, and we can get all the entries of the matrix C. So this is some number, and we want to know what it is because it gives us, if we can show that omega is very small, that means we can have really fast algorithms to multiply two matrices. All right, why do we want to multiply matrices? So if you look at one of the most long-standing best algorithms for matrix multiplication by Coppersmith and Winograd in 1987, it had over 3,000 citations, which is amazing for a theoretical computer science paper. So why is that? Most of the citations, they use this algorithm as a black box. So this is a black box over here. And what type of things can you solve with matrix multiplication? So almost all linear algebraic operations, matrix inverse, rank, determinant, all sorts of stuff, all the linear algebraic things you can solve. Many graph problems, like shortest paths, diameter, regularity partitions, all these things, they can be solved with an algorithm for matrix multiplication because you can represent graphs as matrices. And there's a lot of applications in machine learning, in computer graphics and animation. Basically, everywhere you need to do a change of coordinates, you're going to need to multiply matrices. and optimization, scientific computing, constraint satisfaction, and a bunch of places where you might not even know, you may not even see why they should be related to matrix multiplication, like context-free grammar parsing. You can use fast algorithms to solve parsing, and many, many more applications. So there's so many applications. It's a very basic problem, and we really want to have a very fast practical algorithm for it. Today, what I'm going to tell you will not be about practical algorithms. It will be about what is the best, theoretically best algorithm we can hope to achieve. And hopefully, once we know what the best, theoretically best algorithm is, we'll be able to get to a practical one as well. Okay. All right, so here's a chart of our knowledge about the matrix multiplication exponent omega through the years. So up until 1969, the naive and cubed algorithm was the best. 1969, Strassen came up with an algorithm, here's Strassen, that had a better running time into the 2.81 and completely surprised everyone. And in fact, the way he got his algorithm was by trying to show that you cannot beat 10 cubed. And while trying to show that he cannot beat 10 cubed, he actually beat it. So he got a better algorithm here. Then a lot of improvements happened in between. And then in 1987, Coppersmith and Winograd got this exponent, 2.37548. And then this running time stayed roughly the same up until 2010, when Stodders showed that you can change this 548 into a 369. Okay? And then I showed that 369 can be made in a 288. And Legal showed that this 8 can become a 7. And what we show is that this 7 can become a 6. Now, this seems like a very tiny improvement. So why am I giving this talk? Well, it turns out that the reason, even though the improvement here is tiny, actually what we do is actually we change the method. And the method for matrix multiplication algorithms from here up to here was exactly the same. And we changed it a bit. And basically you can apply this method to many other tensors after that, or many other ways to get matrix multiplication algorithms, and you can get better exponents. All right, so this is the picture. My plan for today, I'm going to spend quite a bit of time introducing you to what matrix multiplication algorithms are like, about tensors and so on, because a lot of these algorithms, they have a lot of technical background, and I'll try not to go too much into detail, but I'll need some detail. Then I'm going to tell you what the laser method is. And then at the end, I'm going to tell you how we improve it. Okay. So here's the matrix multiplication problem again. We're trying to understand what is this omega? What is the best running time we can get in terms of the number of operations over the underlying field so that we can multiply two matrices. We know that omega is between 2 and this number over here now. What we know now is that this matrix multiplication problem is actually about the asymptotic rank of the matrix multiplication tensor. So in the next few slides, I'm going to explain to you what the matrix multiplication tensor is and what this asymptotic rank is. And then we'll see how that relates to matrix multiplication algorithms, and why matrix rank corresponds, like tensor rank corresponds to algorithms. All right, so tensors. Tensors have many guises, okay? They can be viewed as three-dimensional arrays like this, or they can be viewed as bilinear maps. So you take two vectors into a third vector, or they can be viewed as trilinear maps. You take three vectors and make them into a scalar, or they can be viewed as multilinear polynomials. And I'm going to take this last view. So let me define tensors in terms of multilinear polynomials. So let x, y, and z be sets of formal variables, the x variables, the y variables, and the z variables. And a tensor T is just a trilinear polynomial over these variables. So the terms of the polynomial are of the form xi, yj, zk times some coefficient, alpha I, j, k. These coefficients come from the underlying field, like the complex numbers, and they define the tensor. Okay, so for us, this is what a tensor is going to be. What do these tensors have to do with matrix multiplication? Well, every tensor defines a computational problem. What is the computational problem? You have two vectors, x and y here, and you have p polynomials you want to compute. For every k from 1 to p, you look at the coefficient in front of z sub k, which is this term over here. So the sum over alpha ijk xi yj, and this is the polynomial we want to compute. So every trilinear polynomial defining a tensor gives you a computational problem of computing a bunch of bilinear polynomials. Okay, so with this in mind, this is the matrix multiplication tensor for multiplying an M by S matrix by an S by T matrix. And it looks like this. It has a very nice symmetric form. The sum over ijk of xij, yjk, zki. If you look at the coefficient in front of zki, it is exactly the ik entry of the matrix product of x and y, right? So this tensor tells us that the n squared polynomials, or m times t polynomials you need to compute, are just the matrix product entries of an m by s by an s by t matrix defined by x and y. Okay, so this is the matrix multiplication tensor. All right, so the matrix multiplication problem is then a question about the asymptotic rank of this tensor. Now I have to tell you what rank is. So we know what tensors are. They're just trilinear polynomials in this talk, and we have to say what rank is. Tensor rank. Tensor rank is just a measure of complexity of a tensor, and it is the natural generalization of matrix rank. So to define it, I'll just define what a rank 1 tensor is. So a rank 1 tensor is a tensor that can be expressed as the product of a linear combination of the x variables times the linear combination of the y variables times the linear combination of the z variables. So the coefficient in front of xi, yj, zk is ai times bj times ck. We often write this tensor as A tensor B tensor C. If you look at matrix rank, you would just omit the zk's, the ck's, and this product over here, and you get exactly the notion of a rank 1 matrix. Okay, and the rank of a tensor is just the minimal number of rank 1 tensors whose sum is T. So this is just a natural generalization of matrix rank. All right, so a polynomial, a trilinear polynomial, its rank is just a representation as a sum of R terms of this form. Okay, so if we look at the matrix multiplication tensor, it looks like this. So now I want to tell you how the rank of this tensor corresponds to matrix multiplication algorithms. So it comes from this lemma, which I'm going to hand wave a proof for in just a second. So the lemma says that if you have a bound R for the rank of the M by S by T matrix multiplication, that's R, then we immediately get a bound on the matrix multiplication exponent, omega, as 3 times log base MST of R. How we do that? With a recursive algorithm. It's easier to explain when M equals X equals T. In that case, the expression is like this. If the rank of M by M matrix multiplication is R, we get this expression for omega. So how do you prove this? You look at what the rank expression of this matrix multiplication tensor would be if it were R. It's just a sum of R terms that are linear combinations of the X entries times the linear combination of the Y entries times the linear combination of the Z entries. So it gives us a representation of the tensor that looks like this. So what does that have to do with algorithms? Well, let's try to use it to have an algorithm. We have an expression like this for some matrix multiplication problem that has constant size. Think of it as 2 by 2 by 2 by 2 matrix multiplication. Then you can take larger matrices that are n by n and view them as 2 by 2 matrices whose entries are blocks of size n over 2 by n over 2. More generally, if it's m by m by m by m, it will view them as m by m matrices with blocks whose sizes are n over m by n over m. So every matrix has, you can just block it like this, and now you have an algorithm. The algorithm is like this. You look at this expression, the rank expression, and you see that this is a linear combination of the entries of the first matrix, which are now block matrices. And you can compute this linear combination in linear size of linear time of in the size of the matrix, because adding matrices is very cheap. You can compute this linear combination very cheaply as well. It just takes sums of a bunch of submatrices, and this M, S, and T, they're constant size, so it's very fast. And then you can recursively compute this product, this times this, for everyone, for L from 1 to R, for all the R choices of products. So you get R products of linear combinations of this matrix times a linear combination of this matrix. And then you say, well, what do we have to compute? We want the output matrix entry is exactly the coefficient in front of Z sub ki, the ik entry, right? So I look at what is the coefficient in front of Z sub ki in this expression. Well, it's the sum of CLKI times the P sub L, the product here. So it's again a linear combination. And linear combinations are cheap because summing matrices take an n squared time. So the entire computation depends on the number of recursive calls, which is R. And this is exactly where this log base M of R comes from the recursive steps. And this is exactly how Strawson got his algorithm. He showed that 2 by 2 matrix multiplication, that tensor has rank at most 7. Now we know it's exactly 7. And so you get a bound for omega, which is log base 2 of 7. Which is over here. So Strawson showed the rank is at most 7, and so you get omega is at most 2.81, which is log base 2 of 7. Pan showed that the rank of 70 by 70 matrix multiplication is this horrendous number. And then when you took the log base 70 of this, he got 2.80, so less than the bound that Strawson got, so he improved the bound. Now, at this point, people stopped analyzing fixed size matrix product problems because this becomes unwieldy and it's crazy to do by hand. So the method changed beyond that. So something else started to be used. So I'm going to tell you roughly what has been used since Coppersman-Winograd and beyond. So the way matrix multiplication algorithms have been designed since 1987 has had two components. The first component is some algebraic identity, which corresponds to a rank representation of some small tensor. And then a method for analyzing these identities, which is basically a method of getting a matrix multiplication algorithm out of these other tensors. Strawson used the 2 by 2 matrix multiplication tensor, and his identity is the rank representation with 7. And the recursive approach from the previous slide allowed him to bound omega. After 1987, Coppersman and Winograd had defined the Coppersman-Winograd tensor and its powers. So they took the rank representations of the Coppersman-Winograd tensor and its powers and used something called the laser method that Strawson and Coppersman and Winograd devised roughly around then and got their bound on omega. Since then, Stodders, me, and Francois Legal, we all used exactly the same method, but different powers of the Coppersman-Winograd tensor, whatever power means, so we'll define it in a bit. And what we do here is we keep the same tensor, but we change the method. So this is the difference. Before the people were just analyzing bigger and bigger tensors, and now we're keeping the tensor the same and changing the method. All right. Good. So at this point, I'm going to move on to telling you what is the laser method. Okay. The laser method is an indirect way, an indirect method for analyzing getting matrix multiplication algorithms out of other objects, other tensors. It was developed by Strawson, who gave it this name, which has a very interesting, I don't know how it, anyway, there's some reason why it's called laser. Let's move on. So it was optimized by Coppersman and Winograd. And Josh Allman in 2019 showed that if a tensor has the property that the laser method applies to it, whatever that means, then if you can get omega equals 2, so an optimal matrix multiplication algorithm out of that tensor, then the laser method will do it. So in a sense, the laser method is universal for a certain class of tensors. Not all tensors, but for a certain class, if you wanted to get 2. Okay, so let me go more in detail. So I'm going to tell you a little bit about what these indirect approaches to matrix multiplication are. So at a very high level, you take some algebraic problem, P, which has some tensor associated with it, and you show how using a very good algorithm for P, you can also solve matrix multiplication. Basically, it's just a reduction technique. You reduce matrix multiplication to some other problem. But these reduction techniques are very simple in a sense. So let me show you an example. What you want to compute, let's say, is 2 by 2 matrix multiplication, which is basically given 8 numbers. You want to compute, evaluate really 4 polynomials over these variables. But let's say I can solve some other problem P that maybe has more variables and it has more outputs. So I want to be able to embed matrix multiplication into this problem. And the types of embeddings, the type of reductions that all of the laser method applications do, they remove some outputs and remove some inputs of this problem P and turn it into the matrix multiplication problem. What does that mean? In this case over here, I will remove these 2 variables, x33 and y33. This will remove this term. And I will remove this output over here. And all of a sudden, I get all of the 4 polynomials that I wanted to compute for 2 by 2 matrix multiplication as part of P. So you can think of setting these variables to 0 and ignoring this output and plugging all these variables in all the other respective places, and P will compute matrix multiplication. Okay. So I will give it to you in a tensor form now, so you can see what the tensor form of this looks like. You want to compute this tensor, the 2 by 2 matrix multiplication tensor, but you have a rank bound for this tensor, which is a little bit more complicated. It has 1 more z variable and 2 more, 1 x and 1 y extra. And what I want to do now in this tensor, set some of its x, y, and z variables to 0 to get this one. So I get rid of y33 and I get rid of z3. I set these 2 variables to 0 and I get exactly this tensor. This is called zeroing out the tensor P into this matrix multiplication tensor with this notation. 2, 2, 2 zeros out from P. So a very simple lemma says that if you can zero out the tensor P into Q, then the rank of Q is at most the rank of P. And the reason is that you can take any rank decomposition of P, set the appropriate variables to 0, and you will get a rank decomposition of Q. So it's exactly the same rank. So the rank doesn't increase. And so if I can zero out some tensor into a matrix multiplication tensor, then I can also apply the previous bound on omega, which is 3 times log base, the product of the dimensions. And now it's the rank of P over here. So it's a way of upper bounding the rank of matrix multiplication. So this is zeroing out, and this is what all of the indirect approaches do. All right, so actually the laser method is a little more complicated. So it uses the zeroing out, and it actually reduces not matrix multiplication tensor, but direct sums of them into not particular tensors, but powers of tensors. And the 10 powers of tensors, the tensors have to have special structure. So I'll go into more detail in all of these 3. So first, on the next slide, I will tell you how Schoenhage in 81 showed that you can reduce matrix multiplication to computing direct sums of other matrix multiplication tensors. Okay, I will explain this. Then I will also explain how if you have a bound on the rank of tensor T, then you can also get a bound on the rank of its nth power for some definition of power. And this uses recursion. And the laser method does this step over here. It converts direct sums of matrix multiplication tensors into powers of small tensors. And together, when you compose all of these, you'll get a reduction from matrix multiplication to some other tensor. And you get, if you have a good algorithm over here, you get a good algorithm over here. So I'm going to now go over the left part, then I'll go over the right part, and in the end, I'm going to talk about the laser method. Okay. Direct sums. Here, I'm going to define a direct sum. So let T be some tensor like this one over here. I can create two copies of this tensor, basically by renaming some variables, but it should look the same. For example, x2, y2, z2 plus x2, y3, z3 is a copy of T. Just I rename 1 into 2 and this 2 into 3 and so on. But when I take the sum of the original tensor in this one, I will have variables that appear in both copies. So this is just the sum. In the direct sum of two tensors, the variable sets are completely disjoint. So this copy of T and this copy of T have different variable sets. This is the only difference between direct sums and regular sums. So Schoenhagen showed that if the direct sum of k copies of some matrix multiplication tensor has a small rank, then you can bound omega by essentially getting the same expression as if you were working with only one matrix multiplication tensor, except now you get to divide the rank by k. So this is very useful because sometimes you can show that the rank of k disjoint copies of a matrix multiplication tensor is actually smaller than k times the rank of the original tensor. And because of this, you actually get better bounds on omega. So Schoenhagen showed this, so now we're going to use that. So in our picture before, what we have is a reduction from n by n matrix multiplication to this direct sum, so that if you can bound the rank here, i.e. get a better algorithm for such objects, you can bound the omega over here with the correct dependence on R, MS, T, and K. All right. So these are disjoint copies, right? So now I'm going to define what the power of a tensor is, so I can talk about this part over here. Okay. So this is the Kronecker product. So let's say we're given two tensors, they're polynomials, over two different variable sets, x, y, z, and x prime, y prime, z prime. I actually didn't put the extra primes here because it becomes unreadable, but you can think of the primes being here. So S and T are just polynomials with these coefficients, and their Kronecker product is just the product of these polynomials, except the variable sets are merged. So you take the product of polynomials, and the variable sets of S tensor T are just pairs of x variables, one from S and one from T, pairs of y variables, one from S and one from T, and pairs of z variables, one from S and from T. So you take the product of the polynomials and merge the x variables, which are now pairs, well, the y variables and the z variables are now pairs. This is the Kronecker product. You can use the product to define a power of a tensor, which is basically the natural thing, multiplying the tensor by itself n times. Now, notably because of the way we defined it, now the x variables of the nth power are just n tuples of variables of the original tensor, and the y variables are n tuples of the y variables, and so on. So you just get these larger and larger variable sets. Two important lemmas is that if you take, the first one is if you take two matrix multiplication tensors and multiply them under the Kronecker product, you get a matrix multiplication tensor with a product of their dimensions. And this exactly corresponds to this blocking idea that I told you about. You can view an A1 by B1 times A2 by A2 B2 matrix as an A1 A2 matrix with B1 B2 blocks. Right. So this is exactly what this corresponds to. And the second lemma is that that rank is submultiplicative under this product. So the rank of a product of two tensors is at most the product of the ranks. And that's very useful when you tensor tensors. Right? So a nice thing about this, right, is that the rank of the nth power is at most the rank of the tensor to the nth power. But sometimes actually you can get much smaller. The rank of the nth power could be much smaller than the nth power of the rank. One simple example is 2 by 2 matrix multiplication, that it's tensor. the rank of the 2 by 2 matrix multiplication is 7. But the nth power, actually, its rank is n to the omega, right? Something like that, which is not n log base 2 of 7. So sometimes the rank of the nth power can be much smaller. And this is why people define the asymptotic rank. And the asymptotic rank is basically you take the tensor, take the nth power, take the rank, and then the nth root, and take n to infinity. And this can be much smaller than the rank of the tensor itself. And this is used in matrix multiplication algorithms very, very often. Okay, so back to our picture. So we said what this is. We said that you can Schoenhagen reduce n by n matrix multiplication to independent copies of matrix multiplications with different dimensions. And now we can use recursion from the previous slide to reduce the nth power to the tensor itself. This basically just means if you have a bound on the asymptotic rank of a tensor, of course, you'd also have a bound on the asymptotic rank of the nth power as r to the n. And now all we need to do is reduce from this one to this one, and this is what the laser method does. So if we can do that for large enough m, s, and t, and k, we can get a really good bound on the matrix multiplication exponent in terms of this little r over here. So what the laser method does, it takes these tensors T, they have special structure, and uses that special structure to be able to get this the nth power, and in it zero out a lot of variables and get a big disjoint sum, direct sum of tensors that have the same dimension. And then you can apply this technique to get omega. So it's a very specific technique for how to zero out the variables over here if you have special structure in order to get a bunch of matrix multiplication tensors. So, oops. Yes, so now I'm going to talk about the special structure. Right. So imagine a tensor, okay? It looks like this, is some polynomial. And what I'm going to do is take the variable sets of the tensor, the x variables, the y variables, and the z variables, and just partition them in some way, okay? So x is partitioned into L parts, x1 up to xl, y is partitioned to L parts, y1 to yl, and z is partitioned to L parts. Okay, so we've just partitioned the variables, nothing smart. And now we get to define a subtensor. So for every choice of a part x sub I of the x variables, y sub j of the y variables, and z sub k of the z variables, we can define the tensor that contains only those triples xa, y, b, z, c that appear in these respective parts. So x sub a appears in x sub I, y sub a and y sub j, z sub c and z sub k. Okay, so this is just some subtensor. And what we've really done is we've expressed the tensor as a sum of subtensors. For every choice of a part here, a part in y, or a part in z, we have an associated tensor. When you sum them up, they're completely disjoint. Their triples are disjoint, but the variables are not. And the sum is t. We haven't done anything smart. We just partition stuff and re-express t as the sum of a bunch of subtensors. Now, if these subtensors happen to be matrix multiplication tensors, what we've actually done is express t as a sum of matrix multiplication tensors. So we seem kind of close to what we wanted to achieve. What we wanted to achieve is to take t, or some power of t, and get a sum of disjoint matrix multiplication tensors, ones that don't share variables. These guys over here could share variables, but it's still we're on the way there. So we have to get a partitioning of the variables so that the subtensors we get are matrix multiplication tensors. By the way, this can always be done. For example, you can put exactly one variable in each set, and then like this is one of these triples, and this is a 1 by 1 by 1 matrix multiplication tensor. But such a decomposition is not very useful. What you actually want is these matrix multiplication tensors to be bigger than 1 by 1 by 1. And this is one of the special structures you need for the laser method to give you something non-trivial. Okay, we've partitioned the tensor. Fine. So I'll give you an example, just so we're on the same page. Here's the Coppersmith-Winograd tensor. It's actually pretty simple. Q is some number like 5, and is just this polynomial over here is the Coppersmith-Winograd tensor with parameter Q. Why is this tensor useful and interesting? The reason is that Coppersmith-Winograd showed that the asymptotic rank of this tensor is Q plus 2. What's interesting about Q plus 2? Well, the number of x variables is Q plus 2. X sub 0, x sub 1 from up to x sub k, and xq plus 1. So xq plus 2 x variables, q plus 2 y variables, q plus 2 z variables. So actually this asymptotic rank is actually optimal, because that's basically the number of things you have to compute. And if you had such an optimal rank, asymptotic rank expression for matrix multiplication, since the number of variables there is n squared, we will be getting an asymptotic rank of n squared, which would give us omega equals 2. So if we want to get omega equals 2, we should probably be embedding matrix multiplication or reducing it into a tensor like this that has optimal asymptotic rank. So this is one of the reasons why this is used. But anyway, let me show you the partitioning that people use for this tensor. For the x variables, you stick x sub 0 and big X0. x1 up to xq is put into x1, and xq plus 1 is in x2. So x0 and x2 have only one variable, and x1 has q variables. And you do exactly the same for the y variables and the z variables. And now what you've expressed the Coppersmith-Winograd tensor as by the sum of these tensors. 0, 0, 2, because q plus 2 is in z2, t0, 2, or whatever, and 0, 1, 1, 1, 0, 1, and so on. So it's a sum of these tensors. But notably, these are all matrix multiplication tensors. These ones over here are not very interesting because they're just multiplying a scalar by a scalar, and the output is just one output. But this one over here is actually an inner product, because you have a single output, z0 is a single output, and what you're outputting is the sum from 1 to q of xi, yi, so just an inner product, 1, q1, right? And this one's q11, and this is 1, 1, q, so these are non-trivial matrix multiplication tensors, and this is what it's used. Now, if we wanted to zero out some variables here and get matrix multiplication, just a single or a few disjoint matrix multiplication tensors out of this thing, you wouldn't be able to get too many of them, maybe just one. Because if I zero out x0, it will kill off both of these terms. If I zero out zi, it will kill off this one. So no matter what choices I make, I won't really be able to get more than one of these over here. So instead, what the matrix multiplication laser method does is it doesn't zero out the tensor itself. It takes an nth power, as I mentioned before, and zeroes out there because there's more freedom. Okay, so let's take a large power. Remember, T is some tensor like the one on the previous slide, which is constant size, and it's expressed as the sum of subtensors T sub ijk's, and all of them are matrix products. When you take the nth power, you will be the nth power of a sum of Tijk's to the nth power. You open up the sum, and you actually get a sum over n tuples, T1 up to Tn, where every one of these T sub i's here is one of the T sub ijk's that you made the T into. So you get a sum over products T1 up to Tn, where each one of these is a T sub ijk. And there's L choices for I, J, and K, and there's, anyway, so that you have this. Now we assume that T sub ijk is a matrix product, and each one of these is one of the T sub ijk's. And so it's a tensor product of matrix products, which we said is a matrix product. So this sum is also a sum of matrix products, just really, really big ones, depending on n. So we've expressed the nth power as a sum of matrix products. But what we really want is a disjoint sum of matrix products that all have the same dimension. And these don't have all the same dimension unless the TIJKs have the same dimensions. So what we're going to do is actually zero in into some of these terms that have the same dimensions as matrix products. The way we do that is as follows. So you take one of these terms over here. Recall each of the T sub C's over here is one of the T sub ijk's that we express T as a sum of. And now we're going to associate a distribution alpha with each of these terms, each of the products T sub 1. What is this distribution? It is just the fraction of times for every ijk. It's a fraction of times that this term has a T sub ijk in it. So if none of the T sub p's over here in the product is T sub ijk, then alpha ijk will be 0. If a third of them is T sub ijk, this will be a third. And the sum of over all the ijk's is 1 for any particular term. So every term has a particular distribution over the ijk's that it's induced on it. So why do we care about these distributions at all? All right. Well, the point is, if we take a bunch of these products over here that have the same distribution alpha, they're actually matrix products of the same dimensions. Why is this? Well, suppose I have some Tijk that corresponds to a matrix product A times B, A by B by B by C, as the ABC matrix multiplication tensor, and it appears T times somewhere over here. And P by Q, Q by R appears U times in some places. Then when we take the tensor product, we'll get a matrix product that is isomorphic to a product with dimensions A to the T times P to the U, B to the T times Q to the U, and C to the T times R to the U. Right? These is going to dimension. And it doesn't matter where in the product you get A, B, C. Is it here, here, or here? It doesn't actually matter, only the number of them matters. So the distribution, which gives us the fraction of times these Tijk's appear, completely determines the shape of the matrix product that you get. So now our goal is going to be to pick some distribution, alpha, the best distribution, and get rid of all the terms that don't correspond to that distribution. And what I'll get then is a sum of terms that are matrix products of the same dimension. And after that, I will have to get rid of some of them so that I can get a disjoint sum, things that don't share variables. All right, the goal is pick a distribution, zero out variables in the nth power, and you get a direct sum of these terms that correspond to that distribution, so they have the same dimension. The laser method does this, and suppose somehow it gives us L such subtensors. It gives us L tensors that all correspond to this distribution alpha and are disjoint, so they're direct sum. Then we apply Schoenhagen's theorem, which I told you a while back, and you bound omega by this, which is M sub alpha, N sub alpha, and T sub alpha are just the dimensions of the matrix products that, for a fixed alpha. And it's right, alpha determines them. So the only thing that matters in terms of bounding omega, once you fix alpha, is how many of these subtensors you get. The more of them you get, the smaller omega you get. So the goal is to pick the best distribution so that you get as many disjoint tensors corresponding to the distribution as possible, the best number. So we have to analyze, we have to have a method, the laser method, that will tell us how many of these we can get for a fixed alpha. So, all right. So now we have to take a step back and see where we are. So we have this reduction from matrix multiplication to disjoint sums of matrix products. We have a reduction from the nth power to just the tensor. We've partitioned the tensor into a sum of Tijk's. Then we took the nth power and expressed the nth power as a sum of these summons. Every summon has a corresponding distribution that gives us the frequency for each Tijk that appears in it. And then we want to zero out a bunch of variables in here to somehow get a direct sum, completely disjoint copies of these summons that all correspond to that distribution. And because they all correspond to that distribution, they all have the same dimensions, M alpha, N alpha, and T alpha, assuming Ti, Jk are all matrix products. And then we can conclude omega is at most this. And then we have to figure out what L, M sub alpha, N sub alpha, T sub alpha are. Okay, that requires some math. And then we have a problem. What is our problem? The problem is that we're planning to zero out variables. But this distribution alpha is talking about the frequencies of triples, Ti, Jk appearing, whereas variables are just a single I or a single J or a single K. So they don't talk about triples, they talk about single things. So we have to convert the distribution into something that corresponds to variables. So let's do that. We're going to define the marginals of the distribution. Okay. For every variable, a variable block I, we can define the x marginals alpha sub I as the sum over all jk's of alpha I jk. So we fix the I and sum over all the jk's. So this is the x marginal. You can define the y marginals and the z marginals. And this just says the fraction of times in this product that you use T sub p that looks like something that had an I and some J and K here. We don't care what J and K are, as long as the first one is I. The fraction of times you use something with a variable from the ith block. Okay, so now I have to take another step back and tell you that if I take the nth power of a tensor, I want to remind you is its variables are n tuples of variables of the original tensor. So n tuples of x variables, n tuples of y variables, and n tuples of z variables. And since we remember we partitioned the x variables, y variables, and z variables into parts. And this is where the Ti, Jk's come from, right? So x is partitioned into x1 up to xl, y into y1 up to yl, and z is partitioned to z1 up to zl. So the x variables in the nth power, which are now n tuples, are actually partitioned into x sub c1 up to x sub cn, where each of these c sub i's are from 1 to l. So it says basically in the n tuple, the first part of the n tuple, which block is it in? The second part, which block is it in? And the nth part, n part of the n tuple, which block of the original tensor it's in. So we have a partitioning of these variables as well. And now let me tell you what the marginals correspond to. So the marginals correspond to, so for every one of the terms that we're trying to look at, T1 up to Tn, it uses x variables from one of these sets so that they obey the marginals. So the number of times we see I in one of the indices here is exactly alpha I times n. So the fraction of times we see I here is alpha I. So this is what the marginals tell us. So every term here has some marginals that it obeys. And the laser method zeroes out variables according to whether, if they do not have the marginals that we desire. We pick our distribution alpha, compute the marginals, and then zero out variables that don't obey them. And when we do that, we will get a sum of terms so that they obey the marginals. All of their variables have exactly the correct frequencies for every block. And in particular, any term that actually corresponds to our actual distribution that we want will survive. But there could be other terms that survive as well that obey the marginals, but are not according to our distribution. In some cases, this can happen. And anyway, once you do this, the laser method converts these into a direct sum after you have things that obey the marginals. So how many terms can you possibly have in such a direct sum? Well, okay. We're zeroing out entire variable sets. And if we want two of these subtensors to not share any variables, then we want them really to not share the same variable sets. So the number of disjoint subtensors can be no more than the number of variable sets we have, because they have to have distinct variable sets in order to be disjoint. But the number of variable sets that obey the marginals is exactly this multinomial coefficient. It says the number out of these n possible indices in the variable sets, we need alpha 1 of n, alpha 1 times n of them to be 1, alpha 2 times n of them to be 2, alpha L times n of them to be L. So the number of possible things that actually obey the marginals is exactly this multinomial coefficient. And because the number of disjoint subtensors we can possibly get by zeroing out entire variable sets is at most the number of variable sets, we can never get more than m disjoint subtensors. So if we want to maximize how many disjoint subtensors obeying the marginals we get, we should try to get m. And so this is what the laser method achieves, but only under certain conditions. It achieves the maximum number you could possibly get, but under some conditions. The conditions are like this. So remember the marginals, they actually define a linear system over the actual distribution entries. So for every fixed I, the x marginal alpha I is just the sum over jk of alpha I jk. That's just how we define the marginals. But this gives a linear system. For every fixed choice of the marginals, you can define what the distributions that match the marginals are using this linear system. And if it so happens that this linear system has a unique solution, then the laser method guarantees that you will get the maximum possible number of disjoint tensors. So it actually achieves roughly m if this linear system has a unique solution. So basically what happens is that the laser method gives you the maximum number of disjoint things that you can get as long as the marginals of the distribution you're picking actually determines the distribution. But even if they don't determine the distribution, they give you something. So the laser method gives you something. So in particular, it will always give you a disjoint sum of roughly the maximum possible number of disjoint subtensors that are good. So they're consistent with alpha. But if the distribution is not determined by the marginals, it will also give you a bunch of extra subtensors, which are a lot of noise. So let me give you an example of this. So what it will give you is a bunch of a disjoint sum of tensors. Let's say TII means that this tensor uses the ith variables of x variables, the ith y variables, and the iz variables, so that all of these have disjoint variable sets, right? The ones that use the first x, y, and z variables don't share variables with the one that uses the second ones. But then you also have a bunch of these tensors here that obey some other distributions that obey the marginals. And they could share variables with some of these disjoint ones, like this T253 will share variables with the second T22 here, and the fifth one over here, and the third one over here as well. So we have to get rid of all this noise because this is something we don't want. And in all the work up until now, getting rid of this noise costs a significant penalty, so that actually the number of disjoint subtensors is much, much less than n. And in particular, this is what's going on. Suppose that you have m good subtensors and s times m extra subtensors. S is something big, right? Then we have to get rid of the extra subtensors. And when we get rid of the extra ones, we're actually getting rid of the good ones as well. The old approach guaranteed that you can do it and still get m over s good subtensors remain. What we do is actually show that you can get m over square root of s of tensors remain. Remember, s is large. What does this mean for omega? So omega had this expression over here, and L was in the denominator. So if you plug in L equals m over s, s goes up here. S is big, okay? With our new approach, this becomes square root of s. So the bound on omega will immediately decrease. Okay, so from s, you go to square root of s. And this is really how we get an improvement. In all the approaches, you get this mathematical expression, and then you have to go and run optimization software to figure out the best distribution alpha so that you optimize omega over it. Right? Each distribution gives you these m sub alphas, n sub alphas, and r sub alphas, and so on, and you figure out the best distribution. But here, we knew immediately that we'll get a better omega, even without running any software, because we knew that this S is always really big, so it will give us a better bound. So one slide on how we get the improvement. So remember, we have M good subtensors and S bad ones, S times M bad ones. The red ones up here, the bad ones, the green ones are good ones. The old approach to getting rid of the bad ones worked like this. You repeatedly pick one of the good subtensors that shares variables with S extra ones. And there is one, so that because on average, there's S times M bad ones and M good ones, so there is one that shares variables with order S extra ones. And then for all the ones that it shares variables with, you pick some variable that doesn't appear in the good one you want to keep and set them to 0. Now, for every variable that you set to 0, you will be getting rid of one of the good subtensors. Remember, they're completely disjoint and have distinct variable set. So once you kill off, let's say, the second X variable set, you kill off T22 here, but you won't kill off any other. So for every variable, every bad subtensors you kill also one good one. So you remove order S bad ones for every one you keep, and therefore you get M over S good subtensors remaining, and you kill off everything in red. This is just the greedy approach, and this is what we improve. So how do we improve it? Well, it turns out that the probabilistic method suffices. What you can do is pick M over square root of S random good subtensors and work out the math, and you can show that if you zero out every variable that your random sample doesn't use, you will, with constant probability, actually not constant, non-zero probability, you will actually kill off all the bad ones. So you will remove all the extra subtensors with non-zero probability and still have M over square root of S of the good ones remain. And it turns out that for a very large family of tensors, this square root of S improvement is actually optimal. You cannot get more independent subtensors over here while also removing the bad ones. So this is our improvement. How useful is this improvement? Well, it's applicable as long as your tensor partitioning is big enough. And it applies for any one of the powers of the Koppersmir-Winograd tensor after the 8th power, including the best bounds, Koppersmir-Winograd 32. You can go to the 64th power. We didn't do it, but if you go there, you will also improve the bound on omega. You could also apply it to any future tensors as long as the partitioning is large enough to warrant the extra steps that we do. As I mentioned, it's optimal for a large class of tensors. And since the laser method has other applications, this improvement would have other applications as well. So some other applications are in some other questions about tensors and in extremo combinatorics, such as the CAPSAT problem. All right. And one final slide. What's next? As you see, there's diminishing returns over here. We're getting smaller and smaller improvements. And in fact, this is formalized. There's a recent line of work on barriers for Koppersmir-Winograd-like tensors, for the tensors we use. So for example, if you use the same tensor we've been using, even with a slight generalization of the laser method, you will not be able to get better than 2.3725. So maybe you can make this 8 into a 5, but that will be it unless you change the method or the tensor. Also, if you take a vast generalization of all the methods that we have and you still apply it on the same tensor, you will not be better. You won't be able to get better than 2.18. I would love 2.18, so I would totally go for it, but still you won't be able to get to 2. If you wanted to get to 2, what do you have to do? You have to completely change the tensor. You cannot stick with Koppersmir-Winograd-like tensors. I don't exactly know which types you should take. Or you should abandon the laser method and variants of the laser method altogether. And in addition, also use tensors that don't, for which the laser method doesn't apply. As we know that if the laser method applies, it will, if it's possible to get 2, it will give you 2. So if you want to get 2, you have to change the method and the tensors. So that's next. There's a lot of work to be done on how to do this. Anyway, thank you, and sorry again for the technical difficulties. Thanks.
Thanks very much, Virginia. So let's take a couple of questions, and I guess we're going to be splicing the video later. So Cameron asks in the chat about the connection between tensor rank and matrix multiplication. Is it possible that there are omega equals 2 algorithms that don't arise with tensors having low rank?
So I don't see the question, but yeah, from what I understand, it's asking whether this sort of method of going with tensors and rank representations, whether this is the best you could do for matrix multiplication. And the answer is that if you stay in the arithmetic circuit model, where your question is how many operations over the field you need in order to compute to do the matrix multiplication, then this is the best. The rank method is the best. Yeah, so this is a theorem. If you change the question and you say, just in general, what you don't care exactly about the number of operations, but you also allow data structures and other stuff, and you convert the field into like other algebraic objects and do something completely different that doesn't fall within the arithmetic circuit model, then other things could be possible. So this is one of the reasons why people look at combinatorial matrix multiplication algorithms, Boolean matrix multiplication, where you allow other stuff. But so far, these methods haven't been able to even get close to what we can get with the rank bounds.
And just looking at the Q&A stream there that people have posted, one question is about the probabilistic method. Does it only guarantee existence?
Yeah, it guarantees existence. Yeah. If you, of course, if you want to get the actual algorithm, then you could stop the thing at some nth power, where n is actually not an arbitrary variable, but a large enough constant, and then you can kind of brute force over the possible things. You know that an embedding exists, and you can find the embedding, and then that will be your algorithm. You'll lose a little bit in the exponent, but you could do it.
And I guess a couple of people asked the obvious question: if you had to bet, is omega equal 2?
If I had to bet, I say it's bigger than 2. But I'm in good company. Strassen thinks it's bigger than 2. So yeah, of course, everybody else thinks it's 2. So I don't know.
Fantastic. Well, thanks very much, Virginia. That was a really fascinating presentation. Thanks to everyone in the audience also. Please join us for the next talk in the Breakthrough series on August 5th. Yuanzi Chen is going to be speaking on an almost constant lower bound of the isoperimetric coefficient in KLS conjecture. So we hope to see you there. Thanks very much.